I'm Will Burton.
Hi, I'm Stephen Campbell.
Hi, I'm Joseph Angeles.
And I'm Ryan Goodfellow, and this is our BSET 8003 Senior Technical Project. For our technical project, we would like to design a mobile fracking fluid treatment plant. First of all, what is hydraulic fracturing? Hydraulic fracturing is a natural gas process that we can, for harvesting, where we force high pressure fluid into a well that cracks shale underneath the earth to get the natural gas from. The process involves a mixture of water, sand, and other synthetic chemicals called fracking fluid. What is fracking fluid? Well, like I said, it's a mixture of water, sand, and a bunch of other chemicals. 90% of the composition is water, 8% of the composition is sand, and the sand is used to hold the cracks open that allows natural gas to flow up through the well for collection. And the other, about 0.5%, are the chemicals, so acids such as hydrochloric acid, ammonia, methanol, biocides, stabilizers, and inhibitors. The acids will dissolve minerals, the biocides tend to kill bacteria, and the stabilizers keep the clay from shifting and forming. So fracking fluid is mostly water. What's the problem? Well, the problem is that we put millions and millions of gallons of water into these wells, and though 0.44% seems small, it accumulates very quickly and becomes something that you cannot drink, you cannot shower with, and you can't even use it for fracking again. So we've tried to deal with this fracking fluid in the past. One of the ways we've tried to deal with it is deep well injection. As the practice of injecting water fluid deep underground into porous rock formations into these wells. The complication with this is these wells with high injection volumes of water are actually being linked to earthquakes around eastern and central United States, such as Ohio and Oklahoma. Since 2011, occurrences of these earthquakes up to 6 on the Richter scale have been recorded. So we tried to do what we do with all of our wastewater, send it through a municipal water treatment plant. So it gets cleaned, quote unquote, and dumped into a nearby sewer or river. Unfortunately, the water that's flowing out of those plants, it still has elevated levels of chemicals from natural gas production. These plants haven't been updated in quite some time across the country, and they're just not up to code to handle this type of contamination. Same with brine treatment plants. Though in theory, these filters should be able to handle this type of contamination, it just hasn't been able to, and we're not able to meet EPA, FDA, and federal specifications.
All right, so there's going to be a couple considerations within this project. One of the considerations is that we will have a grate that's going to be placed within the first filtering system that will separate the contaminants before it reaches the second filtering system. Another consideration is that we will have 2 pumps, one of them being placed between the reservoir and the stage 1 filtering system, and the second one will be placed after stage 3. We will have this based on a skid design for piping and transportation. We will also have the energy source that will be run off of a generator. We will also have a small catwalk that will be used for easy maintenance rather than a large one. And the waste that's going to be coming from both filtering systems will be placed under the first one so that the second filtering system will recycle it and will avoid contamination. And we will also abide OSHA codes. This is our system block diagram. The first stage, as you see here, will be the holding tank. This is where all the fluid will be stored. The second stage is a second filtering system, which is a second holding tank. After that, it's going to be the third stage, which is the carbon filter, where carbon will be filtered using the where carbon will be filtered. Will be filtering the water through the stage. The fourth stage will have reverse osmosis. The fifth stage will have UV radiation, after which all of the water will be cleaned at a hopefully 98% efficiency. So this is a design concept. here we have all 5 stages laid out in a plan. As you can see, first is the contaminated water, which will be pumped through to the first stage, where a grate, as I said before, will separate the contaminants. The second stage is essentially just a second filtering tank, which is going to recycle all of the fluid back to 2 ports, the waste and the first filtering system. After that will be a third stage where the carbon will filter the fluid through a vacuum pump. After that is just the stages 4 and 5, where it will go through radiation treatment and be filtered out.
So carbon filters have been used for as long as we can remember with treating our water. It's not an uncommon practice, it's actually very well used. Over the past 30 years, we have been able to develop it even more and increase its ability to filter out more and more chemicals, bacteria, and other substances that are harmful to us for potable drinking water. How it works is the molecular surface of the charcoal attracts larger particles and other contaminants. It gets dumped in, and then you have another pump in the center of it that forces it through the carbon and comes out, and then we can direct it to another stage of our system. Carbon is a natural process. The molecules of dissolved compounds collect and adhere to the surface of the charcoal solid, and then when it's done, it's able to attract the forces at the carbon surface to overcome the other forces in the liquid itself. Next is UV radiation, which will be the final stage of our filtration system. The UV radiation is rather new. Before, it was only able to kill, or was only known to be able to kill most of the bacteria and other viruses and stuff. But recently, there have been multiple companies working on creating more powerful UV treatment systems. And out in California currently, there is a water treatment plant that is practicing using this system to actually filter contaminated water, but they're facing the problem where the particles that are going through their system are actually breaking the glass tubes that house the UV radiation filaments. So what is UV radiation, or why should we use UV radiation? This method is currently able to neutralize and break apart some of the chemicals that are in the fracking fluid itself. If we can when we design our system, anything that gets past the carbon and osmosis will hopefully be able to be destroyed in this system, and towards the end it will be potable drinking water.
Okay, so for our system here, we want to use a reverse osmosis system. And reverse osmosis is basically the process of sending the contaminated water, through a semi-permeable membrane through a series of pumps and motors. For our system, we have chosen a tentative system, which is going to run on 20,000 gallons per day, and a bunch of other design considerations here as we move on. It is tentative though, it may change as we continue through our project planning. For our deliverables, we will be working in SolidWorks to complete a model of it, and also flow sims. Our design report will be including, design considerations, a full design report with analysis and conclusions, detailed assembly drawings, and piping and instrumentation diagram. For calculations, we'll be working with fluid mechanics to go through flow calculations, fluid power system design and pump sizing, buckling calculations for the pressure vessels, and also vibration calcs for frame damping. Advanced CAD applications through pipe and stud length calculations and flange design. mechanical system design principles for drive system calculations, heat transfer for heat exchanger analysis, instrumentation for the logic and automation theory, as well as economic analysis for for the bottom line profit. And this is our project. Thank you for listening.
Thank you.